Okay, here we are writing the answer key for the practice test. I will try to go through this as quickly as possible to keep this under, 10 minutes. Let's see. The drawing it right, this is an example of corresponding angles, okay? I won't write that all out. But these don't even have to be parallel. It's just about their location. If you look at this little universe, this is in the lower right. This is also in the lower right. Know those names for those types of angles. Another name for proof by contradiction is indirect proof, or reductio ad absurdum. And that's the old Latin name. Reduced to the absurd. All right? Should know that. Three names for the same thing. The converse of the alternate interior angle theorem says that if two lines are intersected or cut by a transversal, again I'm abbreviating, then if two lines are cut by a transversal such that the AIA angles, the alternate interior angles, are congruent, right? If we've got two lines that are cut by a transversal so that these guys are congruent, then the lines are parallel. Parallel, there you go. A trapezoid is blank a rectangle. Well, a trapezoid is something that's parallel like this and parallel like that. And could that be a rectangle? Well, we have the inclusive definition. So as long as I've got parallel sides like that, these can do pretty much anything. There is a rare moment when they might go like that, and that is sometimes a rectangle, okay? You just got to allow this thing to be flexible, and we go inclusive in our understanding of shapes and names, all right? List all the named quadrilaterals with congruent diagonals. Well, this just takes a bit of study. Rectangles have congruent diagonals. That's how builders make sure door frames are square. Also, isosceles trapezoids like this have congruent diagonals. Basically, it's the thing that have one line of symmetry like that. All right. Using only the variables a and b, find the coordinates of the vertices of these other two. If this is an isosceles right triangle, well, this is dead easy. Make sure you get those. Now the deal is here that we're going up to this point from 0, 0 by going up B and then over A, or over A and up B. But that's the A amount, and this is the B amount. In order for this to be isosceles and right, it has to be the reciprocal, the negative reciprocal slope. Well, here, this slope for this leg right here, that's a rise of B and a run of A. So this has to be a slope of negative A over B. So I just have to go here to get to this point by going down A and then out B. All right, so if I'm going out B this way, that's A plus B. That's just A plus B. And if I'm going down this much, down A, and I'm starting at B, this is just then B minus A. I haven't given myself enough room there, but that's the answer. Okay? Then determine the length of the hypotenuse. Well, that's just the distance formula. From 0 to this is just A plus B squared plus then B minus A squared, and then I'd square root that, and that's the distance of the hypotenuse. Okay, that's all you can do. You can't do anything more than that. You just write it like a formula. All right. Here's a big old proof. I would say you should try to do this by covering up all of the hints. All right, and then if you can do it without the hints, straight up, that would be awesome. But meanwhile, I've given you a bunch of hints, and I'm asking you to draw a diagram. All right, so isosceles triangle ABC with base CA. So if you draw that, I'm going to try to make it big so I can kind of see. there's no wrong way to do this. A, B, C with base, and there's the two sides. I guess, well, I'll make marks like that just now, just to show me that I know what it is. But then it has medians, MC, so that actually is going to be a point. There's MC, that's a median. Know your definitions of medians. We've done a bunch of problems of medians. There's NA, like that. And we are trying to say that these bisect, so we know that this is the same as this, and this is the same as this. We don't necessarily know they're equal to each other yet. Turns out they are. Prove that if they intersect here at point P, that this thing in here is a kite. Well, that would maybe make sense. Here's the proof. Here are the statements. Here are the justifications. I left that out. There, that's a given. I'm not going to waste time with that. Then the definition of isosceles is that AB is congruent to BC. That's pretty much an easy layup. Here, what tells me that AM plus MB equals AB? These two parts make the whole. Parts and whole postulate. And then what tells me that AM is equal to MB? Well, that's the definition of median. And if you want to be fussy, it's really also def of midpoint, because the median hits in the midpoint, and the midpoint says it's two equal parts. Then what says that MB plus MB equals AB? Well, I'm just taking and putting what it's equal to in place of what's up here. So this is just a substitution step. And then what tells me that MB plus MB is 2MB? That's just addition. Combining like terms. Then what tells me that 2MB is equal to 2NB? Well, remember up here I made this step, so this is another substitution. I'm putting things that are equal to equal things equal to each other. And then what tells me that MB equals NB? Well, this is just division property. Division property, I'm dividing both sides by 2. Division property of equality. All right, well, what tells me now, up down here, that angle ABN, this angle up here, is congruent to angle MBC. That's a reflexive property. And then what makes the triangles congruent? I have to keep bouncing back and forth between my diagrams. What makes this triangle? Well, this side is equal to that side. And we've shown that these sides now are equal to each other. And also these sides are equal to each other. And then this angle is equal to itself. So that's side, angle, side. That these two triangles are congruent. All right. It's worth thinking backwards through this. You know, how do I prove a kite is what it is? Well, it has to fit the definition. So I'm definitely trying to show that these sides are congruent to each other here, and that these sides right here are congruent. Well, I've already done that just now, but you want to think through that. So that's my goal. I'm going to have to show these little triangles are congruent in order to show these two parts are. That's really my strategy. I can't show these little triangles are congruent until I've got angles down here congruent. So I have to go through these larger triangles to get there. If you work from the bottom up and the top down, you often meet in the middle. That's the idea there. So BAN, that's this angle down here, angle 1 and angle 2. Wow, that is bad luck. All right, motion activated lights. I love them. Angle 1 and angle 2 are congruent, and that's because of CP, CTC, that these angles are congruent. And then once I've got that, I'm wondering why is it that this angle is congruent to this angle? So that is vertical angles. And then what tells me that these little triangles are congruent? Well, I've got this side here, I've got this angle here, and this angle here, so that's angle, angle, side. Makes these two triangles congruent. And then what tells me that this side here is congruent to that side there, once those little triangles are congruent? Hit it with that CPCTC stick again. And finally, I know it's a kite because I've shown that it fits the definition of a kite. Okay? There you go. All right, in the home stretch. Over 10 minutes. See if I can do this last in less than 5 then. Prove that it's impossible to have a regular polygon with an interior angle of 163. Well, if you've got some polygon that's going like this and it's got an interior angle of 163, that means it has an exterior angle of 7 degrees. Okay, so I'm going to prove it's impossible indirectly by saying this is true. We're going to prove that's true by saying assume there is ... and then say the exterior angle would be 7 degrees, and then the number of sides is given by the formula 360 divided by 7 degrees, and that is, what is that? Let's see. 360 divided by 7, 360, I'm just being lazy here, divided by 7 is 51.4 sides. Help. That's crazy. That's a contradiction. Impossible to have a decimal number of sides. All right, you could write that out. Therefore, 3 dots, it is impossible because we have reached a contradiction. All right, the key thing is showing that that contradiction. All right, finally here, if I am at these points, negative 10, 26, and then up 10, I'm about there for point A. If I'm at 34, 35, I'm about up there for B. If I'm at 73 and negative 17, I'm about there for C. And then D is 13, negative 42, it's about there for D. Alright, so I've got a shape that's like this. Looks like it, I don't know, it could be a rhombus, it could be off by a little tiny bit, could be a parallelogram, it probably isn't a square. But the best way to do it is get out your calculator, find the slopes and the distances, and then look at that. Now, if I do this without a calculator, and I just make these into right triangles like this, I can do those slopes and I can do those distances pretty darn quickly without my calculator. Alright? I like the arrow method here where I'm saying from A to B, how much is it going up? It's going up 25. And how much is it going over? It's from 26 to 34. That's a change of 60. So if that's 25 over 60, I divide by 5, and that's 5/13 slope. All right. Well, what's the slope from B to C? It's from 35 to negative 17. That's 45, 52. So that's a drop of 52. And it's an increase from 34 to 73. That's an increase of, what is that? 39. Okay. So are they reciprocals? Are they opposite reciprocals? I can take a 13 out of both of those, and that's negative 4/3. So they are not opposite reciprocals. All right. But I can also do the distance formula and find the distances. So I'm going to do that to all of these. However, I am running out of time. I got to keep this under 15 minutes.